Hey, AP physicists, this is Mr. Everly talking to you from Canada. Not really, I pre-recorded it. This next part of the unit is about electric circuits, obviously. The first thing you got to know about circuits is that in order to keep current flowing through the circuit, there has to be some source of energy. So the source of energy in a circuit in the diagram is this little guy right here, which we sometimes call the battery. But we sometimes also call that the source of EMF. EMF is kind of an archaic term that physicists sometimes use. It stands for electromotive force, EMF. So this source of electromotive force pushes charges, and traditionally we think of positive charges moving through the circuit, through the resistances, and then back to the battery or the source of EMF. You kind of think of it, as we did last year, like kind of a recirculating waterfall, that the pump is kind of the source of EMF. The water represents the electrons. These little waterfalls are the resistors in the circuit. So the pump pumps the water up to a higher energy level, just like the battery or the source of EMF pumps the electrons up to a higher energy state. The water moves through the recirculating fountain. It hits the first waterfall, falls to a lower level, hits the second waterfall, falls to a lower level. Just like in the circuit, this could be a resistor where the electrons at a high energy state drop to a lower energy state when they pass through the resistor. The resistor gets warm, that energy leaves the circuit in the form of heat, usually. Next, it hits a second resistor, gives up some of its energy, then at its ground state, moves back to the source of EMF, gets pumped to a high energy state again, and does it all over again. So notice no electrons are harmed in the process. We have exactly the same number of electrons we started with. It's just what energy level the electrons are at that makes a difference in the circuit. There's all kinds of sources of EMF. The ones we're most familiar with are like batteries, but you can use a solar panel as a source of EMF. You can use a thermocouple as a source of EMF. Whatever can be used to push those little charges through the circuit. Once again, the charges we know are actually electrons moving through the circuit. But traditionally, and the AP folks use the traditional circuit, the conventional current is imagining that they're positive charges moving from the positive side to the negative side of the battery. Alrighty. So when you build a circuit, you've got a source of EMF, you've got some kind of load or resistance of some type, and there's a couple of rules that have to be followed, and they're called Kirchoff's laws or Kirchoff's rules. The first one says that the algebraic sum of all the changes in potential encountered in a complete traversal of any loop of a circuit must be zero. So in other words, if you pick a spot on the circuit and you go around the loop of the circuit, all the potential gains and all the potential drops have to add up to zero. It's another way of stating the law of conservation of energy. However much energy you put in, that's how much energy you get out. You don't get more, you don't get less. The books have to be balanced from one end to the other. So when you're using Kirchhoff's loop rule, when you're passing through a source of EMF, when you move in the direction of the EMF, now quite often next to a source of EMF, we draw an arrow representing the push. So this thing is pushing charges this way. This is the negative side of the battery or source of EMF. This is the positive side. So you can draw in a little EMF arrow, and if you're moving around the circuit in the direction of the EMF arrow to write your equation, this is a gain. That's a positive number, a positive amount of potential difference. If you decide to move through the circuit this way when you write your equation, because it's totally up to you, When you write this into your equation, it'll be a negative value because you're going from the high end to the low end, okay, as you move through the circuit. The resistance rule. As I go through the circuit, if I move in the direction of the current, it represents a drop in potential. So we see a potential drop here. So we would write into our equation negative IR, where I is the current, R is the resistance, V equals IR is Ohm's law. So a potential drop of IR is what occurs here. If we're moving in the opposite direction, we're moving up the waterfall. We're going up from a low to a higher potential. So if you decide to move this way around the circuit, when you're writing your equation, you put in a positive IR. All right, so in real simple terms, if you wrote the equation for this particular loop, one way to think of it is that there's a point in this loop right here, call it A. And this A, the electrons here or charge carriers at a certain potential. And when we go around the loop, say this way, we would say, okay, as these charges are moving through the loop, at this point, they'd experience an energy increase or a potential increase. So we add on the EMF of the battery. Then as the little guys go around, they encounter a resistor, and that's going to take energy away. So we say minus IR. Okay, again, from Ohm's law, V equals IR, so the potential drop is I times R right there. Then we're coming back to A. Now, the potential at A must equal the potential at A. So if I subtract V sub A from both sides, I better get 0, because the potential difference between A and itself should be 0. So that means the potential of the battery, that is the potential increase caused by the battery, and the potential drop caused by the resistor better add up to 0. And again, that's the law of conservation of energy. If we decide to go around the loop the other way, we'd say, oh, okay, we're going up the waterfall now. We're going against I. So the equation is going to be positive IR, because we're increasing as we go from here to here. We come to the battery, and this represents a drop, because here's the high side, here's the low side, and the pump is pumping this way, so this represents a negative, and it still should equal 0 when we come back to our original spot. So it doesn't matter which way you go around the circuit, whichever is most convenient, but you have to follow the rules. If you're going with the battery, it represents a plus, a positive in your equation. If you're going with the current and you go through a resistor, that represents a negative. Conversely, if you're going the opposite way, you're going up the waterfall, this represents a positive change from here to here, and this represents a negative change from here to here. Again, doesn't matter which way you go, as long as you follow Kirchoff's rules. Okay? One thing you learned last year is that when you have 3 resistors in series, the total resistance is just the sum of the resistors, as long as they're in series. Okay, the book would say something like, add up all the resistors from I equals 1 to N, as long as they're in series, that's the total resistance of the sway kit. All right, so looking at Kirchoff's laws in this particular circuit, we've got a battery, 12 volts. We've got a resistor, 10 ohms, 20 ohms, 15 ohms, all in series. So you could think of this particular circuit as being a battery connected to 45 ohms of resistance. So the current running through this thing is going to be 12 volts across the battery divided by 45 ohms. Punch it out, 0.267 amps of current running through this thing. So imagine the current is going like this. I equals 0.267 amps. Okay. Now, sometimes in the problems, they say, all right, here's point A, here's point B, here's point C. Find me the voltage between points A and points B. You go, oh, okay, what's going on? Well, the potential drop or potential difference between A and B is really the voltage at B minus the voltage at A. So if you're going around the circuit, start here at A and say BA, work your way around. If I'm going in the direction of EMF, that's going to be plus E. If I'm going in the direction of the current, this is going to be minus R1, minus IR1. And then now we've come to the potential at B. So we're not going to go all the way around the circuit. They would just like to know what's the potential between these two spots right here. So the equation is really simple. If I move this over to the other side, I've got E minus IR1 equals VB minus VA. AKA, what's the potential difference between A and B? I put in my numbers, I get 12 volts minus 0.267 amps times a resistance of 10 ohms gives me the potential difference to be 9.33 volts. Okay? Just something they can ask in the problems or in the problem set. Find the potential between two spots. Okay? If you're going to find the potential, say, between B and C, you do something similar. You say VB, work your way around. Oh, we're going through a resistor. Call it IR2 is the potential drop across of him equals V at C. Okay? So minus IR2 is going to be potential difference between BC and VB. So represents a drop of 0.267 amps. Oops, forgot my 7. Times 20 ohms. 5.34 volts. Negative 5.34 is the potential difference between those two spots. Notice we could go the hard way. We could start from B and go around this way. Okay, if we did that, we'd say potential at B. And now we're going against the current, so we'd actually say plus IR1. We're going against the battery, so we're going to say minus E. We're going against the current here, so we're going to say plus IR3 equals voltage at C. So IR1 minus E plus IR3 equals the difference in potential between B and C the other way. Okay, so it doesn't matter which way you go. I certainly would go this way if I'm looking for the potential difference, but you're going to get the same answer if you come around the other way. Next question. What's the power provided by the battery in this case? Okay, well, power is I times E, so that's one way to do it. You could say 0.267 amps times 12 volts gives us 3.2 amps times volts. It's actually watts. Okay. At what rate does this guy turn electrical energy into heat? Okay, we know the resistance, we know the current. So one way to do it is to say P equals I squared R. So we know the current is 0.267 amps. Square it, multiply it by 20 ohms. We get 1.4 watts. All right, so the battery is putting into the circuit 3.2 joules every second, 3.2 watts. The resistors are taking it out, turning it into heat. This particular resistor turns electrical energy into heat at a rate of 1.4 joules per second, or 1.4 watts. Guess how much energy output in heat is created by R1, R2, and R3. Of course, you can tell me right now, it better be a total of 3.2 watts. If you calculated the heat created by these guys per second, number of joules per second, it better be 3.2. Whatever you're putting in, that's what comes out. Law of conservation of energy. One more topic before I move on to the other Kirchoff law is the idea of a battery with internal resistance. Because real batteries are not perfect. What will happen is the battery has a kind of an ideal EMF of, say, 10 volts. And there's also an internal resistance in the battery. Now we represent that as showing like the perfect battery with a tiny little resistor attached to it. So the blue dotted line represents the battery, the Duracell, and what's inside is kind of a representation of what's happening. It's providing us with an EMF of 10 volts, but there's also some internal resistance. So if you were to calculate now what the actual voltage would be across this battery, it's not going to be 10 volts. So for example, if I took a voltmeter and hooked it across this thing, and I've got this 8 ohm resistor sitting out here, what would be the voltage across the battery? Again, not 10 volts, right? So if you want to find out what it is, do what we just did. Say, you know, treat this like A and B and find the potential drop between A and B. Okay, so we could say, all right, the potential drop between these two guys, we're going to find the voltage at A. We're going to move in the direction of the current. The battery is sending current this way. And we're going to say, all right, add on the battery, subtract I times little r, the resistance of the battery, and we'll get VB. So pretty simple. In order to find the actual voltage across the battery, we're going to say it's 10 volts minus whatever the current is times our 1 ohm of resistance. How can we figure out the current? Well, this is just a resistor. This is a resistor, so we have a total of 9 ohms of resistance. So if I equals V over R, the total push in this circuit is 10 volts. The total resistance in this circuit is 9 ohms. So that means we have a current of about 1.11 amps. So across this battery, we don't have 10 volts. We have 10 volts minus 1.11 amps times 1 ohm. So when this battery is in the circuit, it reads 8.89 volts across the battery. So in the real world, when you put a battery across the circuit, there's this load potential difference across the load push versus ideal. So this is a 10 volt battery, but as soon as you put it in a circuit, the voltage across the battery only reads 8.89 volts. If I change this load, that will change the load output voltage of this battery. So in the real world, you've got batteries that have an actual or an ideal load voltage. This example, which I took straight out of your textbook, it's example 27-1, shows something a little bit more complicated, something we probably didn't see last year. For example, we've got a battery over here with an internal resistance. We have it connected to another battery which has internal resistance, and those two batteries are in series with another resistor. So notice also the two batteries are hooked up to fight each other. This one is trying to push our positive conventional current this way. This one is trying to push it this way. Apparently, this one is at a higher potential or higher EMF because the current is actually flowing this way through the circuit. So it's almost as if this battery is hooked up to be recharged. So you got this guy on a charger, this is a source of EMF, and we're charging up this battery. That's one possible interpretation of the diagram. So let's say that E1 here is an EMF of 4.4 volts. Its internal resistance is 2.3 ohms. Let's say our big resistor here is 5.5 ohms. E2, EMF number 2 is 2.1 volts and it has an internal resistance of 1.8 ohms. Okay, let's say the question is, how much current is flowing through this system? Okay, there's a number of ways to approach this. I think probably one way which will help us is to use Kirchoff's loop rule. So for example, if I start at one point in the circuit and move around the circuit, so I decide, okay, when I write my equation, I'm going to go clockwise around the circuit. I'm going to move in the direction of the current. That'll make this very conventional. And if I start right here at this point and start walking around the circuit, I'm going to add and subtract the potential gains and losses. So start here, start walking clockwise. My first term is E1. Keep walking. When I hit this point, I am fighting against this. I'm moving in the opposite direction of the EMF push of E2, so I'm going to say minus E2. Keep going. I know the current is moving in this direction, the same direction I'm walking through the circuit, so I'm going to say that's minus IR2. That's a potential drop. This is also a potential drop, IR. Here's another potential drop, minus IR1. So again, as I move in the direction of the current, whenever I cross a resistor, it's a drop of potential. It's a drop in energy. Okay? The total addition of all the gains and losses is 0. Now check out this equation. I know everything in this equation except for the current. So I could say this is E1 minus E2 minus I times R2 plus R plus R1. Okay, so if I move this to the other side and divide by the resistances, I get E1 minus E2 divided by R2 plus R1 equals I. Punch your numbers into the equation. All our givens are up there. We get 0.240 amps as the amount of current running through the circuit. One other question asked in this example was, what's the potential difference across the battery? So if I were to put a voltmeter across battery 1, for example, what's it going to read? Okay, now this position right here is really equivalent to B. This position here is really equivalent to A here. So if I label them A and B using the labels given in the diagram, I could say, all right, the potential at B as I go around the circuit minus IR1 plus E1, keep walking, equals BA. So in other words, minus IR1 plus E1 equals BA minus VB. So the difference in potential across the battery, minus 0.240 times 2.3 ohms plus 4.4 volts equals 3.8 volts. So perfect EMF in a fantasy world, we'd say, oh, 4.4 volts. In the ideal situation is what I'm trying to say. We'd say 4.4 volts. But this thing's got some internal resistance. So in reality, it's only going to read 3.8.